This is the pre-lab talk for experiment number 10 for Chem 110, electrical conductivity of solutions. The goals for this experiment are to make conductivity measurements of various solutions using the Vernier conductivity sensor. Once we make these conductivity measurements, we'll be able to observe the effects of concentration, ionic charge, ion size, and the chemical nature of the ion on conductivity by making some comparisons. We'll also be able to classify certain samples as strong, weak, or non-electrolytes based on their conductivity measurements. Finally, in the second part of the experiment, we'll get to observe the change in conductivity during a chemical reaction by performing a titration of sorts, where we measure the conductivity versus drop of titrant added. All of those reactions are acid-base reactions. For today's safety pause, we note that we're going to be working with many different chemicals. To minimize the risk of any hazards rearing their head, we want to make sure that we label all solutions very carefully. Also, reagent bottles should be stored in compatibility groups. That is, for example, we would want to keep all of the acids with the acids and all of the bases with the bases. When we store chemicals, something that you don't see very much with the video labs, we often store them in secondary containment bins. This prevents solutions from spilling on the counter as much. They'll end up in a secondary containment bin, which can be cleaned out easily. It is also important that we neutralize all acids and bases before flushing them down the drain with plenty of water. We also note that the acids and bases we'll be working with in this experiment are corrosive, and gloves should be worn during all of our measurements. Of course, although it's not shown here, we always want to wear our safety goggles and our lab coats. You may have talked briefly about ions in solution in lecture. The theory of ions in solutions was first formulated in the early 20th century by Svante Arrhenius, a Swedish chemist, who in his PhD thesis described experiments where he applied a very low voltage to solutions that contain ions. He proved that the ions were there because applying that very low voltage created a current that was measured between two electrodes. This allowed for conductivity to be measured effectively. We'll be doing this experiment of sorts now with a more modern instrument, the Vernier conductivity sensor, which provides a low voltage to the solution, causing the ions to move between the electrodes, conducting electricity. Arrhenius also described three groups of solutions based on the number of ions in solution. These are strong, weak, and non-electrolytes. A very simple experiment can be done, which you might have seen in lecture as a demonstration, where two electrodes are attached to a light bulb. If the solution is conductive, then the circuit will be completed between the two electrodes and the light bulb lights up. For a strong electrolyte, the light bulb lights up very, very strongly. This is due to the fact that all of the compound that dissolves in water is converted into ions. Since there are many ions in solution, you get very strong current and therefore a brighter light bulb. On the other hand, for non-electrolytes, there are no ions in solution, which does not allow for the circuit to be completed. Therefore, the light bulb does not light up. Finally, there's an in-between state called the weak electrolyte, where the compound that's dissolved in water does not completely ionize, forming less ions in solution. You can see in the picture on the right that the light bulb only lights up very dimly, since there are less ions in solution. With our conductivity sensor, we'll be able to put numbers with these observations and be able to tell the difference between strong, weak, and non-electrolytes. The conductivity of a solution is affected by many factors. We'll talk about some of the main ones here that we'll be exploring for this experiment. The first effect is, of course, concentration, or the number of ions in solution. We can predict that if there are more ions in solution, a stronger current will be formed when the voltage is applied, and we'll end up with higher conductivity measurements. We'll get to explore this by looking at different concentrations of sodium chloride solutions and their conductivity measurements, where we can test this hypothesis. The other effect that's important is the speed of the ions, how quickly the ions can move throughout the solution. The speed of the ions depends on a few factors. First, the size of the ion. Generally, larger ions should be able to move more slowly than smaller ions. This can also, at least in aqueous solution, be affected by the hydration shell. When an ionic compound dissolves in water, the water molecules surround each ion individually in solution, as shown in the picture on the right. You can see that in this example, the potassium ions, which are the purple spheres, are surrounded by the oxygen end of the water molecule, since that end is more partially negative and the potassium ion has a positive charge, and the chloride ion is surrounded by the hydrogen end of the water molecules, since chlorine has a negative charge and the hydrogen end of the water molecule has a partial positive charge. When looking at how fast the ion can move, we also want to look at how big that hydration shell is. It turns out hydration shell size depends on something called the charge density of the ion, which depends on the size of the ion and, of course, its charge. And a smaller ion, if two ions have the same charge, such as lithium and sodium, which are both have +1 charges, then the charge density will depend on the size. We would expect for a lithium ion, which is smaller, to have a bigger charge density than the sodium ion, which is a larger ion. This means that lithium, having a higher charge density, will also have a bigger hydration shell, meaning it'll attract more water molecules towards it when it's in solution. This means that effectively, lithium is going to behave as a larger ion since it must drag more ions with it as it moves across the solution. I like to use the analogy of going to the mall with my brothers and sisters versus going to the mall by myself. When I go to the mall by myself, I can be in and out within an hour. However, if I go with my brothers and sisters, they slow me down a bit because they want to drag me to different stores or different places to eat. So therefore, my conductivity, as you will, is a lot higher when I don't have to drag all of my siblings with me. And I have a lot. There's 9 of us. Another thing to look at is the chemical nature of the ion. In this experiment, we'll be looking at some acids and bases, which contain H plus and OH minus ions respectively. Since H plus and OH minus are constituents of water, it is when it moves its charge through the solution, it can cheat a little bit and move the charge without actually moving the ion itself. This can be seen in the GIF on the right, which shows the movement of a proton through the hydrogen bonding network of the water molecules. Therefore, we expect H plus and OH minus to have a much higher conductivity than other ions in solution because of this shortcut it can take when moving the charge through the solution. Another important concept that you may want to review is writing complete ionic equations for reactions in solution. This is helpful when explaining what's going on in part 2 of the experiment when we do the titrations. A complete ionic equation takes all strong electrolytes and breaks them up into ions. This can allow you to see the different types of ions that are present on the reactant and product side, and you can draw some conclusions about conductivity before, during, and after the reaction is complete. Let's briefly look at some procedural points, although more will be explained in the lab video. The picture on the right-hand side of our screen shows the vernier conductivity sensor. Note that it is a slender black cylinder that contains a stainless steel rod, which is a temperature sensor used to measure temperature for the conductivity measurements. The actual electrodes themselves that are used for the conductivity measurements are on the inside walls of the sensor. The box, which is different from when we looked at the temperature sensor, allows us to set the sensitivity of our sensor. We will use the most sensitive setting, the 0 to 20,000 microsiemens per centimeter, which are the units used to measure conductivity in this experiment. It's important that we make sure that the setting is on the 20,000 microsiemens per centimeter setting so that we are able to get nice numbers to compare all of our measurements. Using a lower sensitivity will cause saturation in the conductivity measurements, which will basically make all of them look the same, which we don't want because we want to make some comparisons. In this experiment, we'll also use the events of entry data collection mode in Logger Pro. This type of setup allows us to basically make, for part 1, a data table where we measure the conductivity of our different samples. In part 2, we can use events with entry to do our titration, where we enter the number of drops of acid added for each conductivity measurement. Events with entry allows us to basically record data at different points during the experiment, creating either a data table or a plot. It's also important that we store our sensor in a beaker of deionized water when it's not in use. When we measure the conductivity of a solution, we need to keep a few things constant. Conductivity also depends on the area at which the solution is contacting the electrodes. We want to keep this constant so that we can compare the numbers and have fewer variables to worry about. To do this, we'll be using 150 milliliter beakers, which we will pour in 50 milliliters of solution, basically filling the beaker 1/3 of the way. We'll immerse the sensor in the solution and stir the solution gently with the sensor itself. When our reading stabilizes, then we will press the Keep button, which will allow us to generate our data table. You'll notice in the video that the last digit, which is our uncertain digit, will fluctuate a little bit. Typically in this experiment, we collect class data and calculate averages and standard deviations of the mean. For this lab, we're going to actually leave that out a little bit. It is also important to avoid contamination by rinsing the sensor with deionized water between measurements. This will actually be done in the experiment by swirling the sensor in a beaker of water before putting it in the next sample. For part 2 of the experiment, we'll be carrying out 3 different acid-base reactions. In each titration, we'll be adding a concentrated acid dropwise to 80 milliliters of a more dilute base. We do this to minimize changes in volume, which can also affect the conductivity. Again, we want to make sure that we control our variables so that we're able to look at the trends that we are studying. When we perform our titrations, we're going to make a conductivity recording for every 10 drops of solution added. What we're looking for is the behavior of our conductivity during the reaction, at the endpoint, and beyond the endpoint. To be able to locate the endpoint, we will add bromothymol blue to our solutions at the beginning to make sure we can identify the endpoint. Bromothymol blue is an acid-base indicator that is blue in color in basic solution, which we'll have before the titration, during the titration, and turns yellow when the solution becomes acidic, which will occur after the titration. The color change portion will help us to figure out where the endpoint was. And once again, because we're interested in the behavior after we reach the endpoint, we'll titrate 4 or 5 points beyond where we identify our endpoint to be, or after the color change of the indicator. I hope you guys enjoy the lab video. I know it's kind of on the long side, but I'm trying to provide you a little bit of interesting conversation. So, hope you enjoy.